Greetings and welcome to lesson number 12. Today we're going to be running a SAP analysis. So first, let's review some of the basics of our previous lesson. And right now I'm just going to view pretty much the results of compiling your load cases. So go to define load cases and you can take a look at how I've defined my load cases. So of course I've got the dead load case, and then I have pretty much all my load patterns named as S number, L number, defined through here. I've also included preloads due to the lateral load, so you need preloads on pretty much both decking support surfaces in order to perform the preload. You can't see it here, but there's a lateral pull also, and that's that point load. And then I pretty much have all my load cases and all of the corresponding steps for each load case. So step number 0 pretty much corresponds to the preload. Step number 1 corresponds to the loading applied at load location 1, and step 2 corresponds to the loading placed on both load location 1 and 2. So to give an example, case 1 of course has this particular pattern, and notice I've actually corrected these. In the previous lesson I made a little bit of a mistake. This should actually be not 150 as I'd done the first time. It should be 75, corresponding to essentially half of the load applied to only one side of the bridge, because there's two sides of the bridge. Similarly, step 1 should have the load applied at load location 1, and step 2 should have the load applied at both load location 1 and load location 2. So that's the same with all of these cases going on down step 0 through 2. And then I have case L, which is just a lateral load case, the preload, and then the final result at step 1 once the actual lateral load is applied. So hopefully that makes sense. Now let's go ahead and prep our model to run. So in order to analyze our bridge, you go to the Analyze tab, and you can set your analysis options. Right now we're just going to keep pretty much all of our available DOFs or degrees of freedom active. But you can use this tab if you're choosing to do maybe a 2D analysis, and that can be useful just for conceptual designing. But for right now, just do space frame and it's all these stuff. So now, when we go to Analyze, the other thing that we want to do is set the load cases to run. So by default, it'll run pretty much all of the load cases. I've already turned off the modal load case, but you can toggle which ones you want to run by clicking on the one that you want to toggle, and then say run or do not run load case, and it'll just kind of switch between the two. You can say run, do not run all, and it'll switch all those, blah, blah, blah. I'm going to choose to run the dead load case, and then all of these defined case name types. But these original patterns, the patterns I'm choosing not to run. So I'll just select all my patterns, it should be these, and then I'm going to say do not run those, because they don't really provide anything for me, and if I include them, then they're just going to get in the way when I try to view my results. So I'm not going to run those, I'm just going to run the cases. You could run them, but they're just not very meaningful. So now you have this. I'm going to choose to run now, and this will basically run the analysis for all these load cases. And there it goes, bam, alright, load case complete. And as you can see, it defaults to the dead load case. As if you're curious about which load case is being displayed, take a look here and it'll actually say. So this is the deformed shape of the bridge after the dead load is applied, and you're probably wondering, oh wow, this looks really bendy. This is just the dead load. Look at this lateral, it's like flipping down, it's crazy, there's no way. And no, there is no way. But you can change some of the options for this to make it look a little bit more practical. So in order to view the deflection results, go up to the Show Deformed Shape, and then you can select which load case you want to view. I'll keep it as dead. And here's where the nonsense with the excessive deflections is coming from. It auto-scales to make the deflections a little bit more visible. The default scale factor is, I think, 1,000, at least in this case. It'll automatically scale it, obviously, but what if I were to just say set the scale factor to 1, so the absolute actual deflections that the bridge is experiencing? If I do that, then it looks like nothing is happening. So, I mean, this is kind of why it's nice to have the scale factors, so you can actually see what's going on. So I'm just gonna, I'm just gonna go back to auto, and then it'll automatically do this stuff. Okay, so that's great. If you want to go back to your undeformed shape, you don't want to see this, and you want to toggle between the two, then you can do that, and then check out the deformation going on. You can also do an animation. Ooh, yeah. I don't know why it does the up and down thing. It's just weird. But I don't think you could hear it, but there was also music that played with it. I don't know why they do that. Anyways, so you can flip through all of your load cases that you selected to run and check out the actual output deflections for those. So here I have basically step 1, or rather case 1, step 0, so this is the applied preload. And if you forgot where basically your load locations were being applied for this particular case, you can go back to display your frame loads and then just kind of select which load pattern you want to view. You can actually, or you cannot, I guess I should say, view the actual cases. You can only view the patterns, which is somewhat unfortunate, but that's okay. So you can see where the S1L1 is located at least, and that's right here. And likewise, the S1L2 is located here, just for reference. So here and here. Just kind of burn that in your memory for now. So going back to showing the deflections, I can go to case 1, step 0, and basically we have a preload here and here. And just to make it a little bit easier to view, I'm going to go into like basically an XZ plane viewpoint. So I'm going to select XZ view, bam, and now I have basically a 2D view of the bridge from the side. That's kind of nice. So you can see there's a little bit of deflection locally due to the members and all that jazz. Now that's great. We can view deflections, and check it out. If I go to a particular point, it'll actually automatically pop up with the point object's name and the U1 through 3 and the R1 through 3. So the U1 through 3s are pretty much the deflections in each of those different coordinate directions. So basically 1, 2, and 3 are directly corresponding to X, Y, and Z. So that means U1 is actually the deflection in the X direction, U2 is the deflection in the Y direction, and U3 is the deflection in the Z direction. And as you can see, U3 is a negative number, which means that this point is deflecting down, or in the negative Z direction. So it's not a whole lot, you can see. It's a pretty small number, 0.01 inches. And remember, these numbers will be controlled by what you have set here. So the default unit for measurement is inches. Alright, so hopefully that helps. What can we do with that? Well, you can go to one of your deflection locations, one of these deflection points, and automatically, the nice thing about having your points named is that when you hover over them, you can see this is the point corresponding to the load location for case 1, deflection point 1. Alright, that's great. And we can measure directly what U3 should be, which is negative 0.0225 inches. So that would be the value that you would kind of pluck off and use, more or less. But remember, this is the preload case. So you'd have to go through and then check out the actual final deflections at step 2 for case 1, which ends up being something like negative 0.229. So you would take this particular deflection value and subtract off the deflection due to the preload, and then that would be the actual deflection value that you would use when you were calculating your actual cost. Alright, so now that's mostly deflections. Let's take a look at the loads. So what I just did here was I went to show forces and stresses, and you can look at joints, but unfortunately this just displays the joint forces at your restraint locations, which can be useful if you're trying to determine, oh, well, are these forces big enough to have this particular support slide due to, lack of, frictional resistance? So that might be a good check that you might want to do. But otherwise, you'll almost always want to go to show forces, frames, cables, and tendons. So I'm just going to go to the case 1, step 0, and you can select which particular force you want to visualize. And for now, I'm just going to select axial force, because that's probably the most dominant force that you'll see in truss-like structures. I say truss-like because it's not quite a truss, it's kind of a frame. But most of your forces will be axial ones, and those are the ones that you're most concerned about. Alright, so auto scaling, blah, blah, blah. Go to OK, and whoa, what's all this nonsense? Oh no. Well, again, I'm going to go into my XZ plane just to get that nice 2D view. And then, alright, so what's going on here? Well, all of my red happening here and all my blue happening here are pretty much plots on top of the members of the axial force diagrams of each individual member. So that's pretty cool, actually. Check it out, it just follows along the members just like that. So this is something that you might have done in like a homework or something, I don't know. So red pretty much means a negative value. And as you can see, it already reads off, you can hover your mouse over the member and it'll automatically read off what that value is along the member. And this is negative about 0.1 kips, so about a negative 100 pounds in compression, basically. So negative values mean compression for axial forces. And likewise, blue values are positive, which means they're tensile values. So this member is about, 54 pounds in tension. So as you can see, obviously, we'll get into the details of interpreting your analysis a little later in maybe a different lesson, but you can see pretty much all of our top chords are in compression. That's good. That's what we would expect. All of our bottom chords are in tension, more or less. That's good. That's also what we would expect. And then our webbings, or our tendons, are essentially some combination of those two values. So, and there's a particular pattern to it, and you could probably, maybe intuit your way through this. But again, let's cover that in another lesson. Right now, let's take a look at some of the other options that we can visualize with. So just keeping it with the same case, you can select whichever case you want, and likely the case that you'll be designing for, or case or step, the step that you'd be designing for is either step 1 or step 2. So you can look at axial force, you can look at torsion, but I don't think torsion really has that much bearing on the actual bridge. You can look at shear in the 2-2 direction. Remember, by default, I think it orients the 2 direction, the local 2 direction for a particular member, in the global up direction, usually. Not always, but for most of the members that you'd be concerned about with failure and stuff, then you'd probably be looking at the shear in the 2-2 direction. So that's precisely what you would have here. So this is basically mostly the shear is local to the members on the decking, and that's where the loads are actually being applied. So that's good, that's what we expect. And then there's pretty much almost no shear happening in the rest of the bridge, which is good because we wouldn't want any shear anyways, because we pretty much assigned frames, releases, partial fixity on these members to ensure that they didn't have transfer. More specifically, that was just to release moment, though. These can transfer shear, technically, but as you'll see in the next thing, when we look at moment in the 3-3 direction, that's moment about the y direction, technically globally for most of these members, but really the 3-3 is kind of just for each local member. And you can see there's some local bending due to self-weight of the members. It's kind of interesting to see that, but basically there's no moment being transferred at each of those points where we said, okay, the ends of these members cannot transfer moment. We are releasing moment at those ends. So that's precisely what's happening here, and that's good. So we confirm that releases and partial fixity is performing as we expected. And you can see there's a decent amount of bending actually going on right underneath the location where we have our loads applied. So there's one here, and then there's one here. So this is not so great, but it's good to be able to visualize this and to say, okay, well, we might want to beef up our members along this bottom here because they're experiencing a lot of bending. So one idea might be to just kind of increase the diameter of the tubes that you're using for these locations, because then you're increasing the moment of inertia of that tube, and thus it would be able to handle these kind of bending forces a little bit better. So let's go to next. Well, there's not really much else you would probably want to look at here. Stresses, the max and min, I don't think I really use these. Shear in the 3-3 and moment in the 2-2, you probably would only look at these if you were doing maybe a lateral test. And I'll maybe briefly demonstrate that. So let's go to my load. If my SAP will unfreeze, here we go. Let's go to basically visualizing frames, cables, tendons, and I'm going to go to lateral case step 1. So this is after the lateral load is applied, and I'm going to look at moment in the tutu. Yeah, there we go. So there's not a whole lot here going on, but as you recall, this is basically right where my load is being applied, and then there's some local bending going on in the members because that's, where the force is being applied. There's also some amount of, I guess, bending being transferred through the top chords, which is interesting because we didn't release moment in the 2-2 direction. We released it in 3-3, but it still carries moment in the 2-2, which is good. That's 2-2. Anyways, and likewise, shear in the 3-3 is the force in this direction. And you can see it'll actually plot in the 3-3 direction. So this, instead of plotting up and down, it'll plot side to side, which is in the member's local 2-2 direction. So that also helps to just clarify a lot of directionality stuff if you don't want to have to keep bringing up your Control W to see the local axes. So there's a little bit of shear, not a whole lot. So probably not that big a deal. Alright, so that's more or less the basics of visualizing your analysis. The only thing that I would recommend once you run your analysis, and if you want to make changes to your bridge, let's say I want to change this material section to kind of make it a little bit bigger, and I want to go to define, or rather assign frame. Oh wait, I can't do it. It's all grayed out. How come I can't? Well, the problem is once you run an analysis, SAP will automatically lock your model, and that's just kind of to make sure that I don't know, you don't start making changes to your model, and then SAP won't really know how to interpret the analysis results because it's kind of already geared towards what these members are, at least in terms of their initial sizings. So in order to make changes to your model, you have to unlock basically the bridge. So that will delete your analysis results. Oh no, but yeah, you just have to do it. So you can always rerun your analysis. And it doesn't take that long either. So hopefully that was helpful. I'll kind of go ahead and maybe just upload this if there's room in the Dropbox. Otherwise, I'll just kind of hang on to this one. But yeah, alright. Go ahead and play around with your results. Start visualizing them. Maybe open this file and take a look. And yeah, wow, this was a lot longer than I thought. Alright. Sorry, I'll take off now. Alright, bye.